Look closely at the leaves moving in the wind here. We are now seeing AI models generate sweeping natural environments with a level of photorealism that can easily fool the human eye. The developers behind these systems are making a very specific claim about what we are looking at. They state these models are operating as world simulators. The industry moved from generating slightly blurry static images to producing coherent, high-definition motion in just a few short years. The sheer density of the generated pixels, combined with the smoothness of the lighting, create a highly convincing illusion of reality. But then you notice the glitches. A cat leans down to drink from a stream, and the water flows directly upward to meet its mouth. Solid objects occasionally pass right through one another, or a person walking down the street casually steps into thin air. These bizarre physical impossibilities have sparked an intense debate among researchers. One camp argues that the AI is slowly learning the underlying rules of our physical universe through observation. The other argues that these systems are just massive pattern-matching engines, sophisticated parrots that know what a video should look like, but have no idea what a video actually is. To determine whether we are looking at a true simulation or simply a highly convincing optical illusion, we have to look past the generated outputs. We need to open up the black box and dissect the physics of the model's architecture itself. The first problem engineers faced was sheer computational weight. A standard 5-second high-definition video contains dozens of massive pixel grids. Asking a neural network to calculate the continuous evolution of every single pixel 60 times a second requires a prohibitive amount of processing power. The solution was to stop working in raw pixels altogether. Instead, modern models compress the visual data into a lower dimensional map called latent space. You can think of it as a mathematically dense, abstract dimension where the AI actually processes the information. The system uses a 3D variational autoencoder to compress sprawling raw video frames spatially and temporally into a smaller semantic representation. Inside this latent space, it filters out high-frequency visual noise, intentionally leaving behind only the structural layout, textures, and fundamental motion vectors. By stripping the data down to its core mathematical relationships, the generation process becomes computationally possible. This compressed environment becomes the foundational canvas where the AI manufactures its digital world. Operating on that canvas requires a specialized engine, the Diffusion Transformer, or DIT. This architecture takes the visual rendering capabilities of image generation and merges them with the sequence processing structures used in large language models. The DIT chops compressed video into discrete blocks called space-time patches, 16 by 16 dimensional cubes containing spatial coordinates and temporal flow. Mimicking text generation, it aligns these visual tokens and sequentially wipes away noise, predicting the exact shapes and colors needed to transition frames. But moving sequentially creates a major vulnerability. Over a long sequence, generating frames one step at a time leads to visual drift. The model slowly forgets what the original subject looked like, causing objects to melt, morph, or simply disappear entirely. To prevent reality from degrading into a shapeless blur, engineers added a temporal attention mechanism. This forces the network to compress and explicitly store past keyframes in its memory. If a generated camera pans away from a room and pans back 5 seconds later, temporal attention tells the model to recall the saved layout rather than inventing a new one. This memory structure acts as a makeshift form of gravity. It is a mathematical attempt to force physical consistency onto a sequence of independent generations, keeping the scene tied together over time. The question remains, does piecing together a coherent sequence of frames mean the machine actually understands the environment it is drawing? Researchers built a diagnostic test to find out, called the Physics IQ benchmark. Physics IQ forces models to predict the outcome of highly specific, real-world physical interactions. For example, it provides the AI with a prompt and a starting frame, asking it to predict how a soft pillow will react when a heavy iron kettlebell is dropped onto it versus a light piece of paper. Across the board, current state-of-the-art models, including the most famous systems on the market, fail these basic tests. They generate pillows that compress just as deeply for a sheet of paper as they do for 50 pounds of iron, or dominoes that fall straight through a rubber duck placed in their path. This chart maps the core problem directly. We can see the trajectory for visual realism scaling rapidly over the last 2 years, while the line for physical law adherence stays stubbornly flat. This happens because the mathematical loss functions governing these models, the scoring systems they use to learn, are strictly rewarding visual denoising. The model gets a high score for placing the right color pixel in the right place, but it receives 0 reward for conserving mass, energy, or inertia. Without an explicit physics structure built into the code, these models have to rely entirely on surface-level correlations found in their training data. They know that a falling object should eventually hit the ground because that is how most internet videos look, but they possess no causal understanding of the impact. Generating a photorealistic video is a remarkable feat of computational engineering, but visual realism does not equal physical understanding. Today's generative video models are master illusionists, mimicking the aesthetics of reality. Until their architectures are grounded in explicit physical laws, a true world simulator remains out of reach.